Dear friends, welcome to the third lecture on module 3, where we are focusing on risk assessment and reliability applications. This is going to be the third lecture in module 3, where we are going to discuss simplified fatigue assessment. The long term fatigue damage which is essentially caused due to the sea state model can be expressed by using an exponential distribution. As we saw in the last lecture, essentially we are looking for what is called the S-H relationship, or on the other hand one can also select the parameters in the Hn plot. So, now the 2 segment Sn curve, which can be used for estimating the long term fatigue damage by exponentially distributing the sea state, can be given by a simple expression as we saw in the last lecture. Call equation number 1. Alternatively, if one is looking for a single segment Sn curve, then the damage estimate can be computed by where the second segmental part or the second slope is removed. Now, let us extend this concept for a simplified assessment. Now, we are looking for, let us say, a simplified fatigue assessment. If we assume a long term stress range distribution, so for an assumed long term stress distribution as a 2 parameter variable distribution which can be said as the stress distribution probability is P of S 1 minus exponential of minus of S by delta raised to the power gamma, where S is greater than 0. Based on the variable distribution assumed for a long term stress distribution, the long term damage for a single segment SN curve is given by the, as we saw earlier, A gamma 1 plus for a 2 segment SN curve, the long term assessment is given by m by A 1 plus m by nu z plus n t delta r by A C gamma naught function 1 plus r by nu z is going to be equation 5. Equation 4 for a single segment or equation 5 for a 2 segment, which can give me a long term damage assessment, is actually a method of giving a simple estimate of fatigue damage. How one can say that equation 4 and 5 gives me a simple estimate? Equation 4, 5 give a simple estimate because neither loading nor stress analysis is required to obtain the information. Then what have we done in this case? In this case, instead of that, a probabilistic model for a stress range is assumed. So, in this case, equation 3 gives the 2 parameter variable distribution which is assumed for the stress range. Now, fatigue life estimates calculated from the above discussion or from the above equation may actually vary from that of those expressions what we gave in the earlier lectures, because they will be influenced by what is called as a shape parameter. So, the fatigue estimates, in fact the damage, long term or short term both, will be different from those expressed earlier due to the basic reason because they are influenced by the shape parameter considered for the probability distribution of the stress range. Now, this causes really an ambiguity in the estimate, because the equations where you assume a probabilistic model for the stress range gives me one type of estimates of long term fatigue damage. If I do not assume a probabilistic model and actually incorporate the loading and the stress analysis in total, then it gives me a different kind of fatigue estimate. So, this gives me an ambiguity. To reduce this ambiguity, what one can do? One actually has to calibrate the results. Calibrate the results by comparing it with that of detailed analysis. For a specific case, preferably offshore structures. Okay, that is important. We also said there is one more factor which plays a very important role in the fatigue estimates, that is what we call the effect of dynamic amplification. In case of offshore structures, where essentially they are form dominant, there is always a possibility that the dynamic response may get amplified at a certain frequency bands, because systems are actually designed to remain positively buoyant. The buoyancy force on the system is exceeding the weight of the system itself. So, the system remains afloat. So, the transportation, commissioning, towing, everything becomes simple. When it has got to be commissioned, they can be either ballasted and then deballasted, or they can be anchored to the specific site using DPS, dynamic positioning systems, and the work can be carried out for exploration or production, etc. So, when we have a system which is undergoing a larger displacements because of the wave action or because of the wind action, then there is a possibility on certain frequency bands for which the system is not tuned, it may undergo a large dynamic amplification. So, a system which has got a very high dynamic amplification may initiate crack propagation, and the failure caused by the fatigue damage can become even more serious. So, if the structural frequencies are capable of causing appreciable dynamic amplification factor to the response. I am talking about the structural response. This is very true in case of large compliant structures. Okay, this is very true. This will happen. Then what we have got to do is the SH relationship, what we discussed, need to be modified to account for this effect. But interestingly, researchers showed that the amplification is significant will be significant only in fundamental mode. So, as a designer, one need to be careful in fixing the fundamental mode of the system, because we all know that the fundamental mode of vibration is a structural characteristic where mass and stiffness of the system can be adjusted accordingly. So, that the fundamental mode of vibration, depending upon the modal participation of the first mode, can be selected in such a manner, can be designed rather in such a manner that they will not land up in large amplification factors, because if the design includes a very large amplification factor, then that may add up to the fatigue damage which will be caused by the cyclic load effects on the system. Now, to estimate the dynamic amplification, peak wave frequency is actually used. Then a linear relationship between the wave amplitude which is h and log of this, let us say I will say Tp, peak period. Okay. Log of this is used to modify the so called SH relationship, because we already said that the SH relationship need to be modified if you have to account for the dynamic amplification caused by large compliant structures. So, you need to modify the SH relationship with h and log of Tp. One can use wave scatter diagram to do this. To pick up the peak wave frequency of the input loading. In that case, the dynamic response is given by sigma equals, let us say, f of h and q of h. equation number 4, I mean this will be equation number 6, already we have equation number 4 and 5, so equation 6, where Q of H is a typical dynamic amplification factor and F of H is a quasi static response of the system under wave loads. Now, there is another discussion available in the literature to estimate the fatigue damage, what we call as the spectral fatigue assessment. Which is exclusively useful for offshore structures. We will spend some time in discussing this. Friends, it is a well known fact that the response of a linear system subject to random loads with Gaussian distribution will also remain Gaussian. Although the Gaussian sea surface forms the basis for spectral analysis, the load and the response, the load acting on the system and the response which is the effect of the load on the system can become also non-Gaussian unless a consistent linearization procedure is adopted in the through and through analysis. So, we are not bothered about the response of the system for the fatigue assessment, but we are focused on the stress response of the offshore system. Let us say the stress response of the offshore structure is often assumed as a narrow band process. For which both the 0 upcrossings and peaks will follow Rayleigh distribution. Let us say if T star denotes the duration of the storm, which is assumed to be stationary, then the cumulative fatigue damage of the system on the basis of minor rule is given by D equals T star by T naught integration 0 to stress range Q P of S by N of S, which are the distributions, probability distributions of the stress range ds plus Sq to infinity P of S by N of S ds. Call equation number 7, where P of S is the Rayleigh distribution for the stress range in a narrowband process. The probability density function of the stress range S is given by S by 4 mu 0 e to the power of minus S square by 8 mu 0, equation number 8, where mu 0 is the 0th spectral moment of the stress process. S of t. Let us try to compare this equation with the earlier expression what we had. Now, we are comparing we can understand that m will be equal to T star by T naught, where both times are measured in seconds. Now, subsequently the damage estimate for a 2 segment SN curve for the ith short term C state is given by for the ith short term C state is given by di is equal to T I star by T 0 I 1 by A mu 0 the 0th moment to the power m by 2 8 to the power r by 2 gamma function 1 gamma 0 1 plus r by 2 z plus 1 by c. I am talking about the 2 segment, therefore, there are 2 terms. One is with the slope a or the constant a, other is with the slope c or the constant c, as we discussed earlier also. Mu 0 I raised to the power r by 2, 8 raised to the power r by 2, gamma naught 1 plus r by 2 z, equation number 9. Where z can be the stress range S q by root of 8 mu 0 I to the power the corresponding one segment curve, corresponding damage for one segment Sn curve is given by di, that is for the ith short term C state, is di star by T 0 I A mu 0 I to the power m by 2 8 to the power m by 2. In fact, in this equation also this should be m by 2. Please make a change in equation 9, it should be m by 2. The slope is m and the slope is r here, m by 2 gamma function 1 plus m by 2. So, equation number 11. Now, I am interested in obtaining the total cumulative damage over a period of time. To obtain the total cumulative damage, over a given period of time t, one may sum up the fractional damages due to various discrete short term C states. Occurred or occurring during the period t. Okay, one can sum up. So, let us say for this purpose, let us denote the fraction of time of the ith short term C state over a long duration t. Okay. So, we need to express. So, let us try to express the fraction of short term C state with respect to the capital T, what we are looking for the overall period, so that the above estimates of damage are based on a narrow band model. So, there is a need to apply a wide band correction to this. Okay. So, there is a need to apply a wide band correction. So, in that case, the total fatigue damage during the long term using 2 segment Sn curve is given by d is going to be, I am talking about the cumulative one, I am talking about the total damage over a period of time t. Therefore, I should say it is going to be the sum of I equals 1 to ns lambda I di, that is a factor which is going to make the correction for a wide band, because the process assumed is a narrow band, which I say is going to be t, that is period over which I am looking at the damage, summation of I equals 1 to ns lambda I pi by T naught I of, I am talking about the 2 segment SN curve. So, there are 2 different segments. So, I will use the same equation 1 by A 0th moment raise m by 2 8 m by 2 gamma function of 1 plus m by 2 plus the second slope which is 1 by C mu naught I raised to the power of r by 2 8 raised to the power of r by 2 gamma function of 1 plus r by 2 z, which I can call equation number 12. So, friends, in this lecture we have tried to understand how the fatigue assessments can be easily modeled using spectral estimates. We have also seen how a simplified fatigue estimate can be replaced. Instead of going for a full C state model where the stress range and the load amplitudes are modeled, we have also employed the discussions of equations explaining the 2 segment curve and the 1 segment curve appropriately with different slopes A and C or constants A and C and the slopes m and r respectively. We have understood that how one can easily model and estimate the fatigue damage from the ith C state, which is modeled as a Weibull distribution with the 2 parameter, where the C states or the response stress ranges becomes a Rayleigh distribution. Then once you know the damage caused by the ith C state for a specific case, you want to find the cumulative damage, you can sum them up over a period of time t, where we have shown the discussions for understanding the cumulative damage d for the C state of ith short T states, which we have estimated using a 2 segment as well as 1 segment SN curves. We will extend this discussion for short term fatigue damage in the next lecture. Then we will also discuss a specific case study experimental investigations where we estimated the stress concentration factors and the fatigue damage on tubular joints under different kinds of combination of loads and compared that with the estimates given by the literature and highlighted the difference of understanding between the actual behavior and that of recommended for the design curves. Thank you very much.